Okay, Assalamu alaikum wa rahmatullah. We are going to have our lab 1, the first one, which is crystal structure. It's the first lab you will take in a material science session, and we are going to be conducting the lab sessions online, inshallah, and please follow up with me. I will continue to take the attendance, and I will also ask many questions in between your this lab session, so please stay active during the lab session. Okay? So let's start, inshallah. So crystal structure is our first lab. I want to know everything around us is made up of, there is something. Can anyone guess? So when I said guess, please write it in the chat. The usual answers, I want you to write it in the chat. And if I want to ask you, I'll call your name, okay? Atom, molecules, atoms. Yeah, good, excellent. So we have everything around us made up of tiny particles called atoms. Where the atoms are different, having different behavior in each medium. So for example, in solid, we have atoms which are not moving. In liquid, they are together, but they are loosely bonded with each other. So they are slightly moving. That's why we have liquid. In gas, they are away from each other. So they are flying out around and you cannot catch them. So the idea is in the solids. In the solids, we have it. In the solids, atoms are what? Can anyone guess? Atoms are? Yes, this is kind of tightly. All of your answers are okay. I would like, so for the sake of this lab, I would like to say atoms are patterned. Okay, patterned. Why? Because they are usually following a certain pattern. That's why I want to say patterned, or you can say arranged, you can say organized, you can say anything. So atoms in solid are organized. So how they are organized, this is the whole lab about. Today's lab is about how they are organized themselves in solids. Okay, moving on, I want to ask you the arrangement of solid atoms in a solid matter is called what? Let's the answer is obvious, guys. You just have to read the slide name. So so the arrangement of atoms is called crystal structure. So I want you all to open up your mics at this point. All of you, please open up your minds. And on the count of 3, I want you all to say crystal structure. Okay, ready? 1, 2, 3.
Crystal structure.
All right, good. So
Structure.
a few Ahmads are silent and a few Muhammads are silent. So let's do it again. On the count of 3, all of you should say crystal structure. 1, 2, 3.
Crystal structure.
Okay, Fahad Al-Abadi, sorry you didn't respond back, so but I will not ask you to do it again. So guys, this course, material science, you need to say and repeat these terms very much in order for you to successfully complete this course and not make any issue with in the final exam or during the exam. So remember, you have to say these words to remember them, otherwise you will forget it. So crystal structure is the arrangement of atoms in solid matter. So usually you can see it here on the right side. You can see this box. This is the crystal structure. What the picture is trying to say is this one made up of metal, the saucepan in which you cooked your food. But if you look very closely through microscope, there is small balls which are arranged like this, which is making it a shape. So material elements do not share same crystal structure. If you take aluminum, if you take steel, if you take copper, brass, different material has different crystal structure. Remember this. And it is the crystal structure. So why we study crystal structure? This is this point number 3 here. Why we study crystal structure? We study crystal structure because it may define different properties of material. So if I ask you, steel has a melting point above 800 and another material has a melting point below 500. Why? It can hint directly to the crystal structure. So if the crystal structure is a certain way, it is strong. If the crystal structure is another way, it is weak. So crystal structure defines the properties of materials. So before moving on to the next slide, I want you to remember this point, that not always all the solid materials are fixed in a pattern arrangement. Not always. There are some materials who do not have specific arrangement, and they are called non-crystalline or amorphous solids. Okay, non-crystalline or amorphous solid. Diamond is arranged, Hasib. Come on, it's the most beautifully arranged material. Anyway, but yes, you are. It's. Let's not go into detail. I want to take you slowly, step by step. Okay. Uh, so this is a side note. Okay, not the main point. The main point is this one. So arrangement of materials is in a pattern way. Remember, in a regular pattern is called crystal structure. Okay, if there is irregularity in the arrangement, then it can be non-crystalline or amorphous. Okay, there is something called unit cell. Okay, unit cell is what? Unit cell is an there is something called unit cell, one term, and there is another term called lattice. I want you all to write it in the chat. Unit cell. Okay, can you write unit cell? Enter unit cell in the chat. Right. Okay, the rest of you can copy paste the unit cell that I have written. Yes, excellent. Good, good, good. It became faster. Anyway, good, good. Write it down so you remember, guys. Unit cell, excellent. So unit cell is the overall by the way, if you take one crystal structure, if it's given here, if you cut one section, the overall shape of the crystal structure is called lattice. It's like shakl, it's like the shape. So lattice means shape. If you cut the lattice in a certain way, you will get something called unit cell. So in order to explain this, I need to draw a circle and ask you guys, okay, if this is a circle, and I have to draw some lines here. Guys, I think the foodies here can recognize what I'm drawing. It's something to eat. So, okay, if I draw a pizza here, okay, yes, right, I draw a pizza here, the whole pizza you can consider as lattice, okay? But if I take one piece from the pizza out, it will look like this, okay? This thing you can call unit cell, right? Fahimto? Everyone understand? So the whole thing, the whole pizza is called lattice, and if you take one piece from it, it is called unit cell. Now, let's not go into technicalities, how you cut a piece, why you cut a triangle. There is a way to cut it, but forget it for now, okay? Just remember the terms, unit cell for one piece from the lattice, which is the bigger piece, okay? Good. The smallest group, so here we are reading this this blank. The smallest group of particle in a material that is repeating itself is called unit cell. Yes. So that's the definition. You can say, read it on your own. But I'll give you 5 seconds to read it. The smallest group of particles. Can you read it by yourself without opening the mics, of course, because you will then. Okay, good. I think you have read it. Good, excellent. Guys, I'm really enjoying it. You guys are understanding. So if you have any question, let me know. I can stop and slow down. Wow, another thing. I don't know what to say with this. Okay, before moving on to this one, let's recap what we have taken it while I keep this slide. So I started by saying everything is made up of atoms, which is small balls. So crystal structure is the arrangement of atoms within a structure, okay? So in metals. So crystal structure, we started by giving and explaining what is a crystal structure. It is the arrangement of atoms in a pattern way, in a defined way. Lattice is the overall crystal structure, the whole pizza. Unit cell is a small part of lattice which is taken out from the whole crystal structure or the lattice. Now this thing is coordination number. It is called coordination number. So what is coordination number? Coordination number is the atoms bonding or touching the central atom, and this is called coordination number. Okay, the number of atoms touching the central atom is called coordination number. Okay, remember. So in this case, I want to ask you. Let's ask here Muhammad Ismaili. Muhammad Ismaili, can you confirm with us something?
Yes, doctor.
Again, please. Yes, okay, we'll come to this, Asim. Muhammad Ismaili, can you tell me how many atoms you can see in this picture?
5, doctor. 1 central and 4 surrounding.
Very good. There's 5 atoms in total, remember. And how many atoms, if you put your finger on the central atom and fix it, how many atoms are surrounding this central atom?
Just 4 atoms, doctor.
No, just 4 atoms. Good. So the coordination number for this will be 1, 2, 3, 4. Right, Asim? Do you understand? The number of atoms surrounding the central atom is called coordination number. Coordination number. Now, the coordination number can be different. So let's fill the blank here. In this example, we have how many? We have 5 atoms in total. While the number of atoms surrounding the central atom, so I have written here very specifically the number of atoms surrounding the central atom is 4. Yes, very good. So the coordination number is what? 4 or 5? It is 4. So don't confuse yourself, guys. The coordination number is 4. Thank you so much. Let's give you a harder example and see if your brains are working. So far you have taken so many new names. Crystal structure, number 1. Lattice, number 2. Unit cell, number 3. Now coordination number, that's the 4th new name you understood today, mashallah. So let's take a better example for this one. Muhammad Ismaili, just pray I don't ask you again with this. Okay, so let's take another volunteer this time. Abdullah Hamad, can you hear me?
Yes.
Abdullah Hamad, good to have you, wallah. So I want to ask you, what do you think about this picture? You have a lot of atoms here without any coloring. So I have removed the colors here. And let's check if you can pull out the coordination number for this one. I am sure you will not be able to do it. Tell me, how does it look like? Difficult. It's okay. 8. Some your fellow students are supporting you, by the way. Wow, excellent.
15 are the whole atoms.
Yeah, but I think you don't have to see it all. I'll give you one hint, Abdullah. This is the whole lattice. It is not the unit cell, or it is not one section from it. So you need to see the repeating pattern and keep yourself the central atom.
So 4?
How?
One in the middle between 2, 3, 4.
Then the number of atoms surrounding the central atom.
3.
Okay. The first thing you have to define is which one is the central atom. Okay.
Yes, we do have 3.
On the top.
On the top, in the middle.
Okay. Yeah, let me help you. Let's assume. Okay. By the way, you can take anyone as central atom, but you need to see the pattern, guys. You need to see the pattern, that how the pattern is repeating itself. I think the pattern is repeating itself like this. Okay. Can you see this?
Yeah.
So this is from Allah subhanahu wa ta'ala, that in any metal you will have repeating patterns all around. So if you take any piece of any metal and look at the microscope, it will have repeating pattern. So what you need to see is where is the repeating pattern, and then define and see. Guys, whoever is writing 3 is wrong. Thank you. Keep your genius minds to yourself and listen to me. Thank you. No, I'm just joking. So this is the repeating pattern. So let's define first what is the central atom. So let's see if, for example, if you say this is the central atom, This is where most students make mistake. Can you check how many atoms are surrounding this? So you have another central atom here. You have another central atom here. How many are surrounding this? Yeah, excellent. Hamad, Abdullah Hamad.
Yes,
Abdullah,
doctor.
we are talking to you. You are the star guest in this show.
Yes.
If I keep this red one as central atom, how many it's surrounding?
3, 6, 9, 12.
Take one. Only look at one.
Oh, okay. 3. Oh no, maybe 4. 4.
There is
So
other
3
side
at the
also.
top and 1 in the bottom.
Okay, let me help you guys. You have to look at this, okay? This is the pattern you have to look at. So one central atom is surrounded by 6 atoms at one time. If you look at the other one, you can look at it like this also. So you can look at it in 2 ways. Here, if you look at it like this, it will be 3, but it is the whole thing. There is 3 above it, and there is 3 below it, so it becomes 6. Again, if you look at the central one here, it will be also 6. So at one time, one central atom is surrounded by 6. This is the pattern you need to recognize by yourself. Okay, this is the pattern you need to recognize by yourself. So if I draw this one circle and I draw around it 1, 2, 3, 4, and then I start to repeat this crystal structure. Okay, because sometimes you will be given a crystal structure. So if I start repeating this crystal structure, how many atoms does what's the coordination number? That's the question I will ask. So maybe there's another one here. Yeah, coordination number is 4, because at one time there is 4 atoms which are surrounded by them. Okay, so your crystal structure will be given like this, which you have to get the coordination number from. Of course, with more practice, inshallah, you will get better at it. This is the first time you're here to see this, so I don't expect you to be super genius in this. But let's see. Okay, moving on. All right, some new words, guys. Some new words. I have here something called lattice constant. As you can see from the name, lattice constant, and in the picture, this is a cut taken out from the crystal structure lattice. Okay, if I go back to the slide number 2 here, this is the whole crystal structure, the one from which you cut out a unit cell. Okay, now let's look at what's inside the unit cell. If you look at the unit cell, you need to read the unit cell in order to know its properties and differentiate it from other metals. Okay, so what's the lattice constant? Lattice constant is something which is used to define the side dimension or the size of the unit cell. Okay, it is used to define the size of the unit cell. Can you all write it in the chat? Lattice constant for size of unit cell. Lattice constant for size of unit cell. Please write it by keyboard so you all remember. Okay, that is constant for size of unit cell. Okay, can you all write, guys? By the way, I'm recording the chat, so this chat will make sure you are here or not. So please write. If you don't write, you're not here. Can you see I am writing? Can you all write? So from can you all write, I calculate how many students respond or how many students did not respond. Good, excellent. Excellent. Very good, very good. Okay, so lattice constant is for the size of the unit cell. Why I said size is not the appropriate word to say, by the way, but it is good to see how you are going to size your object. So in this case, let's have a look at this example. I have A on one side, so A is one dimension. It can be this also. So you can say this is B, and it can be height. So if any cube, you have 3 dimensions to make it 3D. In this case, do you all agree about this expression? A equals to B equals to C. Guys, what do you think? Did I write something true or false? True. Why do you say it's true, guys? Why do you think it is true? A is equal to B equal to C. Because it's a square. Yes. If it is not a square, it will be different number. Okay. So in this case, we can say A equals to B equals to C, and also it means A is this one. This is also A, and this is also A. Okay. Now let me give you something new. If I say that this is, so let's make it with the different color. Hold on. If I tell you that this blue line is the radius of this atom, okay, because in unit cell you can see the atom has been cut from many sides, so it's no longer look like a ball, it has a slice already. But if I say this this line here, I call it R, okay, R, which is the radius of atom. Can you tell me what is the R value? What's the R? How does the R look like? You can find it out, guys, from your mathematical skills. Don't tell me the answer, guys, don't tell me answer, but I just want you to think that can you find this R value if I give you A using some mathematics or trigonometry or what? Don't give me answer, just say do you think it's possible or not? Because as far as I see, this whole thing on the left side is a complete R. For example, if I take it from here to here, it is, I think, 1R. Now I have so many R's here. 2R. This is another one. 3R. 4R. Okay. So I have 4 R's here, which means I can make this full blue line as 4R. And then we can also draw one line here. So you guys tell me this. The red line is what? Can you tell me the value of red line, guys? A. Good. So the red line is A. Okay. The black line is also A here, and the red line is A, and this is the 4 R's, yani 4 times the radius of atom. So I think we can, have you heard about the name before, guys? This,
I can get it also by Pythagoras, right? If I am not mistaken.
yeah. Can you have you heard about this name, guys? Thank you so much for helping me. Pythagoras formula or Pythagoras theorem. Yes? Yes, very good, very good. So guys, I think we can get, if you can use your Pythagoras theorem magic, you can get or guess that we can get this expression by having this formula, right? 4R square equals to A square plus B square. From this, you can calculate the value of R if I give you a constant. Good. So the idea of this slide is to show you how unit cell can help you find the radius of an atom. Good, interesting. Oh wow, you guys didn't knew you can calculate the radius of atom. Okay, excellent, excellent work. So I think you are getting it. Alhamdulillah. Let's move forward. So before jumping on, I want to show you that there is many types of crystal structures, and there is many types of lattices which has been recorded by experiments, by looking through microscope, by discovery, many things. But inshallah today we will study these 4 crystal structures. Okay, simple cubic, body center cubic, face center cubic, and hexagonal closed packing. If you study these 4, inshallah, you will get enough knowledge of how to calculate the atomic radius, what's the relation between A and R. So these things you can calculate easily for all of them. But for your reference, we have a lot of them here on the right side. The simple cubic is what you were looking at. If you put another atom in the middle of simple cubic, it becomes body center cubic. If you put one atom on the side face of the cube, like a dice which you used to play for board games, it's called center cubic. If the unit cell is a little bit longer, it's not yani cube, it is rectangular, it becomes this. And there is many. So But the beauty is this, mashallah, this learning about material science also makes you closer to Allah subhanahu wa ta'ala, because you can imagine if I found a metal here which is aluminum. For example, if I found aluminum in Qatar, it will follow the same crystal structure which you will find in Canada, or which you will find in Pakistan, or which you will find in America. Anywhere in the world you go, aluminum will follow the same crystal structure, and it's repeating itself. You cannot change it. And that's why this property of the symmetry and the symmetry of atoms is the same throughout. How you are maintaining it, that's the question. So that's the beauty of nature, mashallah. So that's a little bit background about the crystal structures. I think you already understood these terms. I will just make you remember some of them. So we started by saying crystal structure. What is crystal structure? Is the arrangement of atoms in solids. We have a whole lattice, which is the complete crystal structure. If you cut the lattice by some way, you will get a unit cell. Inside the unit cell, you can see, in the crystal structure, you can see the repeating will give you one central atom. If you calculate the atoms around this central atom, you will get coordination number. For the unit cell, you can use the unit cell to calculate the lattice constant, which is the A, used to measure the side dimension, the size. And you can also use the lattice constant to find the R, atomic radius. In addition, there is different types of unit cells available and different sizes of crystal structures available. It depends on which element you're looking at. Okay, so that's the basic theory of this lab, inshallah. And if you have any question, please tell me. Everything is clear, alhamdulillah. If you're understanding, I'm going the correct speed, please tell me. Okay. Thank you so much. Thank you so much. So now I'm going to load a video for you, which will be good here. So let me minimize this. So hold on. I'm going to load the video, which is good and interesting for you to understand how the crystal structure is working. It's going to explain you how they slice to make unit cell. Okay, very important to watch this video. It's good to show you how they are slicing the crystal structure to give you the unit cell. Okay, let's start with this one.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, Any particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center.
Guys, I want you to notice something. Here, I want one thing which is very important is to find out how many atoms does the unit cell made up of. Because when you slice it, each atom becomes a small portion. But how many atoms are there in a unit cell? That's a really important number to find out. So there you can find it here now. Okay? In this example of body center cubic, BCC, you will see it that it is 2. Okay, so let's play it again.
The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below, for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell.
Okay, guys, I think you got the visual explanation of this. Why I showed you this video in order to show you how visually you can put these things in perspective. I know it's difficult to imagine because all of them are balls and looking like different same things. So, but the idea for you is to see how the arrangement will affect different properties of the same crystal structure. Okay, as you can see in the video, he have mentioned about the volume inside each sphere or the unit cell. This makes a big difference because if there's less volume, it means it's very tightly packed together, so it is very strong. Okay, so that's the major thing I want you to focus on in this case. So let's come back to our slides here, and I'll share with you what's the assignment of this lab, as well as share with you different things in this a little bit more. So we have viewed the video. Here. I hope you understand what's being said in the video. So in your lab assignment, guys, you are asked, so the lab work is individual, guys. I'll explain to you how you will do it. Thus, in your lab assignment, you're to work on 4 different crystal structure sizes: simple cubic. The next is body-centered cubic. The next you have is face-centered cubic. And the last you have is hexagonal closed packing. I want you to work on them and find three properties for them. Okay, coordination number, which is the number of atoms surrounding the central atom. For coordination number, you need to look at the whole crystal structure, the whole lattice. You cannot get the coordination number from unit cell because unit cell is already cut. The number of atoms in the unit cell, that's the second thing you will find. So number of atoms in unit cell, as explained in the video, it is the number of atoms you can find within the unit cell. So you have to join the atoms, cut pieces of atoms together to make it, find out how many unit cells you have. And the last thing you have to find is the relationship between atomic radius and the lattice constant. So A and R, as I explained in the beginning of the slides. So you have to do it for all four of them, and you can see it gets difficult. So simple cubic is the easiest one, and then you go to hexagonal close-packing, it becomes more difficult. Okay, good. Do you want me to give example of one how to do it, guys? No, it's clear, alhamdulillah. Okay, good. There are majority. All right, let's see. Okay, I'll just quickly go.
You made it clear, but I just want to make sure, like.
Okay. Let's give you quickly one example. What I will do is I will give you example from each one of them, so you see them also, and you know how to solve it also. Okay, and then I will show you the lab report, how to solve the lab report. Okay, so let's give you one example, or let's give you a lab report first. No, let's take you from here. So here I have simple cubic. In order to get the, let's find the most difficult for this, so it's easier for you. I want you to work with me. So let's see, I'll get another volunteer here, Abdurrahman Muhammad. Abdurrahman Muhammad.
Yes.
Abdurrahman Muhammad, good to hear your voice. Can you work with me?
Yes. Sure.
Khalas? No offense?
No, it's fine.
Oh, you can totally disagree. Okay, no problem. Anyway, okay, I want to find the relationship between A and R. So A is here and R is here. The R is given here in the unit cell. So in order to find this relationship between A and R, you need to look at unit cell. Okay, remember, this is unit cell. Here
okay.
You also need to look at unit cell, and here you need to look at the whole net or crystal structure.
Mm-hmm.
So now let's look at the A and relationship here. The A is the full side length given here, the A. The R is this one.
Yeah, so
can you
2R equal 1A.
Oh, but right, I have this space in the middle.
What space in the middle?
This one. So still A is equal to 2R?
It should be. I mean, if you're talking about what is it called? The side, yes, it does equal, but in the middle, no, it doesn't.
Yani, but A and R relationship is equal to 2R. Okay, I think you're doing this. You're taking the R and dropping it here, so you cut A into half. And then you're taking this R and you're dropping it, cut it to this half, so it becomes
basically
A
yes
equals to 2R. Okay, so guys, you need to work with your magic skills of trigonometry to find this relationship. Very easy. Okay, this is the simple cubic example. Thank you, Abdurrahman Muhammad, for your support. Thank you. Now next one we have is body center cubic. You can see the body center cubic crystal structure has one atom here in the middle, and it has 1, 2, 3, 4, 5, 6, 7, and one at the back, 8 pieces, small pieces around it. Okay, so let's find the number of atoms per unit cell in this case. So can you help me with this, because you need to look at unit cell. Okay, so in the unit cell I have one central atom, which is this one, the blue one. So the blue one, guys, is one atom. Okay, you guys are saying there's more, so let's think what is more. The other one, let's make it green. I'll find the green ones here first. So one, I have 1 quarter, 2 quarter, 3/4, 4/4. It makes 4. Then I have 5, 6, 7, and 1 at the back, 8. So if I join these 8 pieces, it will give me another 1 atom. Do you agree, guys? Or it will give me 2 atoms? This is 8 pieces. Or so some guys are thinking 4 pieces will give me 1 atom. So you decide first. 4 pieces is 1 atom or 8 pieces is 1 atom? Okay, the power of imagination. 8 pieces is 1 atom. Okay, good. Thank you so much. If you cut a ball into like this, it will become 8 pieces. Okay. So the number of atoms per unit cell, in this case, now our answer will be 2 atoms per unit cell. Okay, very easy. You just need to take the unit cell and draw it like this, or you can write it like this also, guys. You can write it like this, so it's easier for me to understand. 1 plus 1/8 into what? 8 pieces into 8. 1/8 into 8 equals to 2. Do you understand what I write here? It means 1/8 into 8 plus 1 is to 2. I just write it like this to make you understand that 1/8 into 8 is the side corners and 1 is the central one. Okay, don't confuse yourself with this. Let's move to the next example. In the face center cubic, guys, in the face center cubic here, I have again given the third point. Okay, let's keep this riddle for you now. I'll go to the most difficult one, which is this one, hexagonal close packing. So let's find the coordination number in this case. For the coordination number, guys, again, for the coordination number, you need to look at whole lattice. Okay, you need to look at the whole lattice because you need to see the repeating pattern of all the atoms and then decide how many atoms surrounding the central atom. In this case, I want you to look at this box here. You can see it is AB, AB. So it starts repeating after AB, AB. Can you find for me the coordination number in this case? Let's draw it like this, and then here you can, this is how you should draw to see, or there's another way also, or this is how you should draw to see. I know the coordination number is the difficult part, but try to get the coordination number now. And I give you one hint, the central atom is the blue one. 18. Wow. If you do 18, then what's your central atom? Okay. All right, guys. There is you need to look at it like this. You need to first decide what's my central atom. In this case, our central atom is the blue one here. Now the ones surrounding the blue one are 1, 2, 3, 4, 5, 6, and 3 above it. These 3 are just above it. If you look at this picture, these 3 are just close to it. So 7, 8, 9, 10, 11, 12. So our coordination number is 12. Okay. So in order to look at the coordination, find the coordination number, you need to look at the whole lattice, the repeating pattern, and then decide what's the coordination number. Okay, this is going to come in midterm, this is going to come in quiz, maybe in the lab, everywhere else. So please focus, pay attention to this one. All 18. Okay, good. But this one is like this. So coordination number here is 12. So I give you example from each one of them. If you want to read more about this or learn more about the unit cells crystal structure, you can go to these links given at the end of the slides. Inshallah, you will benefit more if you read more about it. But now let's me share with you what is required from you in the lab report. Okay, take a break. Let's take a break of 15 seconds. Relax, and then we can come back to the lab report, and after I explain this, you can hear free. Okay,
Doctor,
Aywa.
I have a question. How we determine the relation between R and A? I didn't get it. A equals
The relationship
R in the first example.
The A equals to 2R because the guys draw triangles around it in their mind, and they found if you make the 2R, it is becoming the side length A. It can be A equals to 4R also. It can be A equals to 6R, or it can be A equals to under root A times BR also. Asim, it's not always A equals to 2R. Okay?
Yes, I know it's not always, but how I know, that's what I asked.
Okay,
If
how
it's
for
A
this
equal to
example
A equal
specifically?
4. What?
In this example specifically, you are asking?
Yes, I explained to the previous example, and I will relate with other
Okay,
examples.
here. Okay, it's simple. If I bring, can you see this R here?
Yes.
This the red marker. If I make a arc from here and come to A, and if I make another, this is also R, right? What do you think?
Yes, yes. I got it now,
So
I think. Yeah.
so if I bring it down like this, is it A equals to 2R?
Yes, yes. Okay.
So it's different depending on different case. In this case, it's different. In this case, it's different. You can see here, the A here cannot be 2R. Can you see? This is one R. This is another R. It's not 2R. If you bring it down,
It's
you
gonna
have
be
this
4R,
empty space.
right?
Don't give hints, guys. This is your work to do.
Oh, okay.
Okay.
Sorry.
So,
I had a question, Doctor,
Go-
if you can,
Hatim, please.
about the coordination number. The atoms surrounding the central one doesn't have to be directly bond with, right?
It is directly bonded, but it's to show you it's just expanded. If you look at the unit cell, check. If you look at the lattice, this is directly bonded. This is just to explain they exploded.
Oh, okay.
Okay.
Okay, thank
Yeah.
you.
Good. All right.
Engineer,
Yes.
I think there is one example without the whole structure, only unit cell.
Yes. Very good. Yes, you find it out. Internet.
Okay.
Okay, I didn't give everything. Don't worry. What you have to do is this, guys. Everything I will explain. What's the due date? How you do it? Everything. Okay. I want you to use your newly bought brand new printer, which I asked you last week to buy it. Okay, and print this lab report. How many pages it has? So let's look at it from far away. It has page number 1, page number 2, page number 3, and page number 4. So you print this page and then you start filling it. So please make sure, I'm very careful in the formatting. If you miss on formatting, minus 50. Anyway, so I want you to write your lab numbers here. This is lab section number. So some of you has B03, some of you has B01, but it should be correct. Please make sure that. Experiment name, I want you to write it by your hand, okay? Crystal structures, okay? So this is lab number 1, crystal structure. Formatting is the way you put your system. So for example, if I formatting means this, I ask you to write your student name, you write your student name here, you name your student ID, do your signature, write the date, and leave this one empty, okay? And submission date is the date you will submit your work to me. So it's 28 January, something like this. The due date for this is 6 days. Remember, this is due on Saturday, okay? Saturday by 11:55 p.m. at night, no issue. But I should get Sunday morning, I should get it. Please complete the lab reports on our computers. No, it is printed and done by hand. Very important. And I need, there is one note here. Let me finish, guys, and then you can ask questions. Thank you. Student name and signature should be handwritten at the end of each page. Remember, at the end of each page, you should write your student name and signature. So let's see, where is it? Let's go to the next page. Here, guys, I'm explaining. You don't need to do introduction. Introduction is written here about the crystal structure. Everything is done. What you have to do is fill this information. So the first thing you have is simple cubic. Write, I want you to write the coordination number here, and then you have to write number of atoms in unit cell, and here find out the relationship between A and R for the crystal structure, which is simple cubic. So what students ask me is where they should draw the diagram. So for the coordination number, guys, you need to look at the whole crystal structure. For the number of atoms per unit cell, you need to make only the unit cell. And for relationship between A and R, you also need to draw only the unit cell. Okay. And this is the same you will repeat for body center cubic. And at the end here, guys, please make sure you put your by your hand, and you put your signature here by your hand. So at the end of each page, I need this, and then you will scan it using Office Lens, as I explained in the previous lab. Okay, guys, I will tell everything. Please stop disturbing everyone else in the chat. I will explain everything. Wait. So here, in the face center cubic, I have the same thing. You need to repeat the same. On the second page, you have for the face center cubic, draw the coordination number, number of atoms per unit cell, and this is the unit cell you will draw here and find out the relation. Okay, I want you to show all the steps here in the calculation. Okay, show all steps, and if there is a Pythagorean theorem, you will use Pythagorean theorem and show me all steps. Okay, I need to see how you find the A equal to R relationship. If the steps are missing, you will not get the full mark here. Okay, marks are written there. And here you have the last one, which is hexagonal close-packing. Write your student name here and the signature here. The last page, so now the page number 4, the last page, what you have to do is you have to draw the crystal structure here. Very important. This is not the unit cell. This is the crystal structure. So you will draw the whole crystal structure here for all of them. Okay, all of them, draw crystal structure, the whole crystal structure. And the last question, which is question number 3, you will write down this. Give an example of an item, product, or material, for example, for our daily life, from our daily life, for the following crystal structure. So simple cubic, what is the items I have in my life or in my daily life, which is following simple cubic structure? And do not write the do not only write product name, mention how it is following the crystal structure. For example, if you tell me it is the cooking kettle where you make tea or chai, but tell me cooking kettle may a cup of aluminum or may a cup of steel, something like this. Okay, so give example from our daily life, very important. And that's it, guys. It's all drawing and some sketching and calculation. So remember one thing, in question number 2, you will draw the whole crystal structure, but in this one, the question number 1, here you will draw the unit cell, because you need unit cell to find A and R relationships. Okay, this lab is due on Saturday 30th. Okay, this is due on Saturday. Hold on, let me finish, please. Saturday 30th January by 11:05 p.m. Okay, this lab report is due on Saturday 30th January by 11:55 p.m. I will put the recording of this session also on Blackboard, so if you miss something, you can go back and review. Okay, thank you for your time in this lab session, and now you are free to ask any questions one by one. Thank you.